Hi, folks. My name is John Garamov, and I'm a senior principal engineer at AWS. I've been with AWS for about 7 years, and in that time, I've worked on a variety of systems, variety of service-oriented architectures, where one of the services in the system operated at a pretty large scale. And today, I want to talk to you about the risk of overload in such systems, specifically the risk of a large service overwhelming the smaller ones with a large volume of requests, causing it to fail. And then I want to share with you a number of patterns we've used at AWS to prevent such situations by putting the smallest service in control. But first, why do we build service-oriented architectures? Splitting your system into services is a pain. You have to think about things like APIs between services. You have to pick serialization protocols. You have to worry about transit network failures. And honestly, debugging problems in such architectures is still not as easy as it needs to be. So why do we take on that complexity? Well, we do it for a couple of reasons. The first reason is blast radius. When multiple loosely related components live inside of the same monolithic application, then a failure or a bug in one of the components can spread and bring the entire application down. And that's not good for our availability. We can certainly do things like put a lot of effort into isolating components from each other, and we can spend a lot of energy on testing, but time and time again we'll learn that when there's a shared surface area, that surface area can be used for failures to spread. The second reason has less to do with technology and more with sociology or with the human behavior. Getting a group of people to reach consensus and to agree on something can be challenging. And anybody who's ever had to have their group of friends pick a restaurant for lunch has probably experienced that. And there's certainly examples where that's possible. And as the teams, that the same problem happens to software teams. And as the teams and applications grow larger, the problem actually becomes worse and becomes more challenging. And for that reason, a lot of times organizations choose to organize themselves, to split themselves into smaller teams and have each team own an application or a service. And then the teams have to decide on APIs between services, and they have to have those discussions and agree. But beyond that, each team is capable of making its own independent, autonomous decisions on their service. And they can choose things like different programming languages or different application frameworks, or even decide on how they want to do their code reviews or how they want to perform their stand-ups. And they can do all of that without having to consult or coordinate with other teams. And that's good for agility. At AWS, a common way to organize applications or services is into services that are responsible for the data plane functions and services that are responsible for control plane functions. And if you've been following us, you've probably heard those terms before, and there's certainly a fair amount of ambiguity around them, and especially one person's data plane can be somebody else's control plane and vice versa. But the way I tend to think about them is that the data plane is where you, as a customer, get your value out of AWS. These are your EC2 instances where your applications run, or your RDS instances where your relational databases are living, are stored, or even things like S3 storage nodes where your files and buckets are stored. And the control plane is there to manage the data plane. It performs functions like accepting customer configuration and propagating it to the data plane servers, or pulling operational state from those servers, detecting operational problems, or taking broken or bad service out of service and replacing them with the healthy ones. And if you look at your own architecture, you may find analogies to the control planes and data planes as well. And what most of these architectures have in common is that the data plane, the scale of the data plane, is much larger than the scale of control plane. And we want it that way. It just wouldn't be a very economically practical system where the control plane was as large and as big as the data plane. And one way to build such a system is to have your control plane expose a set of APIs, and then perhaps it's sitting behind a load balancer of some sorts. And then the data plane servers could be calling these APIs, and they could be polling for the latest customer configuration updates or publishing some operational state. And this tends to be one of the simpler types of distributed systems to build, and that's good. We like simple systems because simple systems have great inherent availability advantages. But if you're not careful, this type of system also comes with a availability risk where the larger data plane can overwhelm the much smaller control plane, causing it to fail. And to illustrate that, I want to talk about an example that many of us are probably familiar with, calling a school phone number. Here in the US, most schools and most school districts have a phone number that families can call. They can call those numbers to do things like report absences or ask about their kids' grades or even perhaps talk to a teacher. And on the other end are school receptionists or school employees who are answering those phone calls, and they're either answering the questions or they're routing the question to the right person. And just like a control plane, the school employees are outnumbered. There's a lot more parents, a lot more families in the typical school district than there are employees answering the phones. But on most days, that's okay. The phone calls from families, the phone calls from parents arrive at random, uncorrelated times, and they're evenly spread out throughout the week. And perhaps occasionally two parents would call at the same time, and one of them may either have to wait on hold or will hear a busy signal and try again later. But the system is stable and it's making progress. But if you've ever lived in a northern climate, then you might also be familiar with a snow day. And as a kid, snow days are awesome. You get to play in the snow, and then on most typical snow days, the school is also canceled. And therein lies the problem for our outnumbered school employee. On the morning of the snow day, most families wake up, and the first thing they need to do is they need to find out if their school is going to be open or closed that day. And if the phone call is the only way for them to do that, then they're going to pick up the phone and they're going to dial that number. And what used to be a randomly distributed volume of calls coming in from the families turns into a very highly correlated spike of calls happening at about the same time in the morning. And our school employee, who was never scaled to handle a volume of calls, very quickly gets overwhelmed. And we see this behavior in other places. We see it in a airline customer service during weather events, or we see it in a ticket sale sites when a major sporting events or major artists go on sale. And we see that in software systems as well. Typically what happens is that a very subtle change in an environment changes the behavior of the large fleet in such a way that all the servers in that fleet that used to be acting in an uncorrelated random fashion all of a sudden start acting in a very correlated way, all acting the same way at the same time, overwhelming the smaller servers with a high volume of events. And there are a variety of triggers for that. It could be things like recovery from an outage, where the large data plane fleet needs to contact the control plane to find out about its state and what it needs to do. Or caches are notorious causes of this behavior, where a very subtle change in the cache hit rate can cause a very big impact on the volume of calls to the downstream service. So what does such an overload situation look like? If we were to plot such an overload, we may expect to see a graph that looks like this. At first, as the volume of concurrent requests on the system increases, the system is doing more work. Its goodput, or its ability to succeed, its ability to do useful work, increases as well. And then we may expect that eventually the system will reach some sort of ceiling. Perhaps this is number of servers behind a load balancer, or perhaps this is number of receptionists that are answering the phone calls. And then we'd expect that eventually the rate of work will flatten and the system will continue making progress. And that doesn't seem so bad, because eventually we'll make it, the system will make its way through the backlog, and all the parents will get their phone calls answered, or all the data plane servers will get their configuration updates, and the system should return back to normal, should return back to the steady state. Unfortunately, that's not what happens in real world. The overload graph for most systems looks more like this. As the concurrency in the system, as the load in the system increases, most systems have a breaking point beyond which additional request, additional load actually causes the system's goodput, its ability to do work, to decrease. And in most systems, it drops very quickly to zero. And that seems counterintuitive, but there's a lot of, we see that behavior in a lot of systems with different architectures and different fields. And the reason for that is subtle. And a lot of it has to do with the fact that as the concurrency increases, the system is able to spend less and less resources on individual requests. And eventually, these requests start taking long enough that the client would have given up waiting, and worse yet, probably would try again. Queues are another notorious triggers of this behavior, where as the queue builds up under load, the requests are sitting in the queue waiting. And by the time the request makes it to the front of the queue, the client, again, probably have gone away, timed out, and maybe even tried again. And this behavior is actually pretty familiar, pretty well known in the networking world, where it goes by the name of congestion collapse. And a lot of effort, a lot of energy has been put thinking about how to avoid these situations, how to manage them. So what can we do? The most straightforward pattern, the most straightforward approach is to apply some sort of load shedding. If the system knows where a breaking point is, then right before that breaking point, it can start rejecting additional requests. And it could be doing things like either throttling or potentially bounding its input queues, where if the queue is full, additional requests are rejected. And that can be successful, but to a point, because at certain scale, at certain load, just receiving a request and rejecting it takes enough resources out of the system that it still suffers an overload. A much more successful strategy is to have cooperating clients. If the clients are actually able to cooperate, and if they can detect when the system is suffering an overload and back off and throttle themselves and actually send fewer and fewer requests downstream, that can be actually a very successful strategy at mitigating overloads. And this is how TCP/IP networking stacks operate. It's been a tremendously successful pattern. But getting the clients to cooperate can be hard, and in some situations are just impractical. So next, I want to talk about three other patterns, three other approaches that we've been using at AWS that help us mitigate the overload by avoiding the imbalance of load, by avoiding the situations where the larger service can actually dictate the pace of work to the much smaller one. To talk about the first pattern, we actually don't have to stray very far away from the school example. These days, my kid's school actually doesn't require us to call a number to find about snow closures or any other closures. Instead, on the evening of the snowfall or the morning of the snowfall, the school publishes periodic updates to multiple social media sites. And then they direct the parents to go to the sites to find out about the latest status. For these social media sites, thousands of parents reaching out or opening connections at the same time is just not a big deal. These sites are scaled to handle millions of concurrent requests. And for them, the snow days in a typical school district may not even register above noise level. And we can apply this pattern to our control plane and data plane interaction. At Amazon, the service we use when we want to serve content at scale is Amazon S3. And we typically start by having the control plane periodically pre-compute its configuration and then upload it to an S3 bucket. And then independently, the data plane service can reach out to S3 and they can pull this configuration updates and apply it locally. And the pattern can work in the opposite direction as well, because the data plane service can periodically, once again, upload their internal operational state to yet another S3 bucket, and then the control plane can go to that bucket, download the configuration, and do what it needs to do with it, do some processing. And because S3 is scaled to handle even the largest client fleets, this pattern, the data plane service, all reaching out to S3 at the same time, are just not going to overload it. And because of that, this is actually a very popular pattern, because in addition to having inherent resiliency to overload situations, it actually turns out to be relatively simple to implement. It doesn't require a lot of sophistications on either the data plane or the control plane software. And in addition, as the size of the data plane grows, the control plane can stay relatively small, and that's a desirable property for these kinds of systems. But unfortunately, it doesn't work in all scenarios. In some situations, the configuration that needs to be propagated to the data plane just may be impractical to pre-compute ahead of time. For example, if every data plane server gets its own personalized configuration and that configuration needs to be computed dynamically based on the current state of the data plane software or data plane server itself, it just may not be practical to pre-compute this configuration ahead of time and upload it to S3. In other examples, the changes need to flow from the control plane to data plane as fast as possible. Like in control plane for the Elastic Container Service that needs to propagate a new container launched by the customer to the data plane in milliseconds. And And just writing it to S3 and pulling an S3 file just doesn't allow us to reach this kind of density, this kind of propagation times. And in these situations, we'll look to another pattern we see in schools these days. In addition to publishing periodic updates to the social media site, my kid's school is actually also able to call the families with latest notification, latest updates. At the beginning of the year, the school collects the phone numbers from all the families, knows where to reach them. And then when events like snow days happen, school system dials in those numbers and it pushes the either pre-recorded, sometimes even an actual person talking on the other side, but it pushes these events down. It owns the rate at which the connections to the families are opened. And it may take a little bit longer to work through the backlog. And on a particularly bad snow day when there's a lot of closures, it may take longer for some families to receive their notifications than others. But because the rate of this notification, the rate of this outgoing connections and this outgoing phone calls is driven by the school system, it is unlikely to suffer an overload in such situations. When we apply this pattern to real-world systems, we typically look at examples where we can have the control plane own all the interactions and own the rate of all the interactions. And it starts with the control plane opening a connection to the data plane servers. And once the connection is open, that connection can be used in both directions. It can be used to push configuration updates from the customers to the data plane server. And it can also be used to pull operational state from the data plane server for later processing. And the important thing is that the control plane fleet, the smaller control plane fleet, owns the rate at which that work is done. It owns all the actions, and it drives the rate at which these actions are done. This pattern is more challenging to implement because we want to make sure that every data plane server has a connection from at least one control plane server. It does require the control plane to keep an up-to-date inventory of all the data plane servers. And the control plane needs to make sure that each control plane server equally divides or nearly equally divides the portion of the data plane fleet that it will be managing. And that requires some sort of coordination. And coordination in distributed systems can be a hard problem. And it could lead to problems like zombies and ghosts. And this might be funny sounding words in the context of a software system, but these are real problems for services, for systems like that. A zombie is a data plane server that is alive, it's up and running, but the control plane doesn't know it. It thinks it's dead. And because it doesn't know about the data plane server, it is not opening connections to it. It is not pushing configuration updates. And that can be problematic for these systems because we now have a data plane server. We might be having a data plane server that is running with potentially stale configuration. And ghosts are the opposite of zombies. Ghosts are the data plane servers that are dead. They're broken. Perhaps they have broken hardware, or perhaps they've been taken out of commission. But control plane doesn't know about that, and it is trying to open connections, and it's failing. And if we're not careful, that itself can cause a knock-on effect and failures. And to deal with zombies and ghosts, I want to talk about our last pattern today. And this is a pattern I've been seeing more and more lately in real world, and I'm actually a big fan. And it starts by having the large fleet submit a very lightweight form asking for a callback. And the form has to be lightweight enough that submission of the form alone doesn't cause an overload. And then the customer service department, upon receiving that form, can do one of two things. And if there is enough capacity in the system, if the system has enough idle capacity, perhaps there are enough agents or enough outgoing phone call slots, the system will call back on the number provided by the customer. And most days when I click the submit button, the phone call rings almost immediately. But if the system is under load, or perhaps there's a lot of incoming volume of calls, or there is a bad day at the customer service because there is a lot of returns or a lot of phone calls coming in, then it may take longer. And it may take longer for the full callback to occur, but the important thing is that the rate of these callbacks is driven by the smaller fleet, it's driven by the much smaller customer service department. And because of that, it will control the rate and will be resilient to overloads. The way to apply this pattern to our system, the way we tend to apply this pattern to our system is that we start by having each data plane server send a very small UDP message to a random control plane server. And the relevance of UDP here is that Unlike TCP connections or TLS handshake, these UDP messages are extremely lightweight to process, and they're unlikely to cause an overload. Even most typical software that haven't gotten any optimizations can handle on the order of tens of thousands or even hundreds of thousands of those messages. And then upon receiving of such a UDP postcard, the control plane server can do one of two things. If it has enough capacity and if it's not under any particularly high load, it will go ahead and open a connection to that data plane server. And once it opens the connection, it will use that connection to push configuration updates and pull operational state. It will be in control of the rate of the work. It will own the rate at which the work is done. And if that particular control plane server happens to be under load or happens to be perhaps too many connections that are open or too much work going on at the time, then it will ignore the message. And the data plane server will try a different control plane server next and keep doing that until it finds somebody who is able to open a connection. And because in this pattern, the control plane doesn't have to keep a up-to-date inventory of all the data plane server. It doesn't have to know which data plane servers are out there. It is more resilient to problems like zombies and ghosts because we're just not gonna. The data plane servers are the ones who own the initiating the connection. They are the ones who own advertising that they are out there that are willing to accept a connection. But because all of the actual work, all of the connection opening and the change and messages flowing with those connections are driven by the control plane, it has similar resilience to overload as the previous pattern. So what are my takeaways? I want you to take a look at your systems and see which ones of your services are analogous to control planes and which ones are analogous to the data planes. And when you do that, pay attention to the relative scale of the two. And if the scale is about the same, then by all means, keep your current architecture. Don't complicate your life because time and time again, we see that simple architectures have great impact on availability of the systems. But if you do find out that your data plane outnumbers your control plane by a factor of 100 or more, then take a look, see if you can use one of these three patterns to put your smaller control plane, to put your smaller fleet in control of the rate at which work is done in the system. Well, this is it. Thank you very much for listening, folks. And please do not forget to enter session feedback.